Hello, good afternoon. Is my voice audible to the online participants? Okay. So we'll begin this session by the for participants who are not having the access to the Param Shakti Param Vidya system. So um, we'll start by installing Linux into the virtual box and then installing the MPI subroutines in the Linux subsystem. So there is a link already shared in the Teams chat window. The online participants can also refer to that, but I will briefly go on. So firstly, we'll download the VirtualBox software from the website virtualbox.org. So download the VirtualBox 6.1, or there may be a newer version also available. So as you can see, the version has been updated from while recording the video to version number 7. So you can download this. So after downloading the VirtualBox, you can install the VirtualBox using this set of instructions. So click on next, then again next, and install the network interfaces. Install. So this is the interface. Next, we'll download the Ubuntu ISO. So search on Google or any other search engine. Get Ubuntu, accept all. So we have like Ubuntu 20.04. So let me just check the newer version. We can see 22 is available. We can download that. So moving on, click on the download button. So coming back to the VirtualBox interface, click on new. Then we have to give the name of the virtual machine and then attach the ISO file. So in name, we put the name of the OS. In machine folder, we have to give the hard drive. So this is an image file for the dynamically allocating machine image. Then we specify the memory size here. So we can specify to 1/4 of the laptop size. And then we click on next. So these all can be put as default. And then in the processor, we go to system and then processor. We can give how many processors we want to virtualize. So you can put this to 1/4 or 1/2 of the system processors available in your laptop. So in display memory, you can max it out. So after that, click on start. We will click on Start. So in the dialog box, we will click on Install Ubuntu. So basic keyboard layout English US, continue. Normal installation. And we'll disable the updates while installing Ubuntu. And then erase disk and install Ubuntu. And click on Install Now. Hit continue. Then click the time zone if interested to Kolkata. And you can fill this form. Then the installer will start installing. And then restart now. So after restarting this machine, cancel this. Okay. So next we'll install some packages such as Build Essentials, DKMS, Linux headers. We can also update the system. So continue. And then you can restart once. And then from the drop-down menu, go to Devices and insert the guest editions. So that is a nice feature to have. So run the guest edition. Then again restart the system. So then afterward you will get the full screen. So for MPI installation, we'll demonstrating here the MPI CH library. So sudo apt install MPI CH. Press Y. So we will demonstrate a hello MPI program. So to compile the program, we will use MPI CC and then the finding. And to run the program, we can use MPI run. Number of processes to executable. So hello world is getting showed up from 2 processes. We can also change the number of processes to 4, and 4 processes would be shown. For it also it will be shown, but it will take some time because we have given 2 number of cores into it. So this is the MPI installation demonstration. Now I will hand it over to Debjyoti Kumar for cluster purposes. Hello. Hello. Okay, so what Nathan showed was if you are not able to have the access to the system, or you don't have access to any other system rather than an MPI, that was the way you can run your codes. Okay, since it's the hands-on session. So how many have access to this? Great. Okay, so and those who don't have access, how Nathan showed, you can install, you can have VirtualBox, and there you can run Ubuntu and run the codes. So for any queries, please write it in the Q&A chat, Q&A in the Teams. Okay. Those who have access to that. So first of all, so to access this, you have to SSH minus P4422, then team1 at that for okay, after that, this captcha will come. This then the password. Okay, so first, has everyone logged in into the system? Those who have access to this, logged in, right? Okay. And did everyone get the files, the MPI files? The files. Name okay, so those who have access to team 1. Okay, there the files are in MPI layer 3, then final. Okay. Siddharth will be giving the files to all the other members also. So just wait a second. So first we will be going through. So there are 2 ways of submitting the jobs here. One is interactive mode and it is a non-interactive mode. So first we will be seeing how we will be submitting the jobs to run the code.
here in this system. Okay, so team one guys, team one, those are team one, they can access the files in final API H3 final, and for the other teams, they will be given the files. And online, I think it has been uploaded in Teams. So those who are in online, they can get it from Teams. No, everybody will get. So just wait for a few minutes. You will get the files. Okay. I will tell you. Just wait for a few minutes. So I will be basically showing first how to. I will be showing how to run a code. I will be writing a hello world code, and there I will use a script file, which looks somewhat like this to submit the job. Okay, I will explain this, and then you can run the code. You submit the code yourselves. So let me just in the meantime explain what this is. So to submit the jobs, we have to use the command sbatch dot the script file. Okay. So inside the final folder, there will be a readme file. So inside the final folder, there will be a readme file. Okay. So there I have given the commands how to run the code. So for since the files are given to you, don't have to copy it. Okay, so the file for compiling the files, it is for if it's a C code, if it's MPI CC file name, minus o, then executable name. Okay. So for example, if I have hello world.c, okay, I want to compile this file. So what I will do is MPI CC, since it's a C code, hello world.c minus o, then the name of the executable. So I'm writing hello world only. Now, if I do ls to C, you will be seeing there is a hello world, a free file hello world, which is the executable file. Correct. So to run the code, the command is mpi run minus np is the number of processes that you want. Say I want 2, and then the name of the file, executable file, which is hello world. If I do this, if you just see these 2 lines, it is showing hello world from 2. Okay, but we will not submit the jobs like this. Okay, we will submit it using sbatch. So if I go to this file, so what it says, this is basically a way of getting the allocation you want. Okay, so how many processes you want, how many nodes you want, and on how many cores you want to run. So this is a way of getting the allocation and then submitting it. This is a non-interactive way of submitting your jobs. So the first command you can see here is saying now nodes one. So we have in this system 2 nodes basically. Okay, so if I just do S info, you can see there are information about the partitions given, right? You just if those who have access to ParallelProgramming can do it yourself. Just do S info. So this basically gives the information of the partitions that are present. So if you see, we have CPU partition and nodes 2, right? So that means we have 2 nodes, and each node has about 48 cores processes we can access. So here it's saying I just want 1 node, and in that one node, I want 2 processes. TechTalks is basically saying how many processes you want. All right. So for those, say if I want to run API code on the 30. Okay, so you have to mention it TechTalks equal to 30. All right. Or if you you can take the maximum also. So the maximum here is 48. So then you can inside a single for this node only, since you have taken nodes equal to 1, it will give in 48 all the codes to access for your access, and then you can run your reports up to 48 processes. You can make this 2 also. So here in this system, we can have maximum 2 because this system has 2 nodes maximum. So you can have 2, right? And 2 nodes enters 48. So basically, you will get 96 codes. So you can check your code or run your code to maximum 96 on this system. Okay, I think Siddharth has sent the files. So please check if you have got the files. The final, files in the final folder. Everyone got the files? Anyone who did not get the files? Everyone got the files? Please put your hands up if you have got the files. Got the files. That's it. Got the files. You have access to this? You have access to Teams? So this said everybody got the files, right? Right. So please now put these files inside your ParallelProgramming cluster system. So if the easy way is you can use WinSCP here. Using WinSCP, you can just transfer the file. Okay.
सबको सेंड कर देता तो अच्छा होता फिर मुझे फिर वो कॉपी करके बीस में फिर मतलब हर एक दिन में मैंने पढ़ लिया एमपीआई स्कूल डेली हर एक उसके दिया पर मुझे हर एक
Hello. So you have npm k3 folder, right? In every accounts. Yes. So you have a MPI K3 folder in all your team accounts. So there you go to final. So inside MPI K3, go to final. CD final. Is everybody there? There you can get all the access to all the codes. All right. So just so there is a job.sh file, right? So first do one thing. Everybody just compile the hello world. So MPI cc hello world dot c minus o hello world. Okay, so if you are having any issue with this, please raise your hand. If you are getting any error. Anyone tried this compiling the codes? Okay, just those who have access to this and those who have got the codes, just take one thing. If you have what is the module present, do just module list this command. What is the module present? Just check once. Okay, good. If it's Open MPI or compiler in PHPC 20.7. This, or you can also have module dot compiler. You might also have this. Okay, so anyone is okay in the module list.
For accessing Paramvidya, you should be connected to internet.
Okay, so anyone comparing the code here. Yeah, display. We can do that, but this is. Yeah.
So that is
Yeah. So in the everybody there is a. Everyone, there is a readme.mpi, readme.mpi.txt file here in your folder. Can you find that? Inside that, there is a compile command. Inside that, there is a run command too. Right? So the codes you have to compile using the compile command and then the run command. First just compile the code. Just those who are able to compile the hello world, just put your hands up. Let me see once. And those who are having issues with compiling. Here, compile. What is the issue? So compilation, that side F1 compile, right? What is? So you can, those who have compiled, just you can check, just run this, write this command sbatch jobs.sh. So this basically means you are submitting the file for running. Just do this and submit this just and see what is happening. Submitted it. Okay, so those who are having. Okay, let's just once those who have done SBatch, you will get a number, right? That is basically the job number that you have submitted. All right. To check what is your output, just do vi job dot then the number that you have got job number. I have got 2421. So if I do 2421 dot out, I will basically get the output file. Okay. So I will repeat once more. Those who have done sbatch jobs.sh to submit your file, submit your code, you will get a number which is a job ID. The job ID will be unique to everyone. Okay. So just do vi job dot to job dot your job ID dot out. So if you do this, you will see there it is written hello world from process 0, 1 and 0 and 1 and the number of processes is 2. Okay, coming back to compilation. So those who are having issues with compilation, I'm just repeating the compilation command. It's MPI CC hello world dot C -O for the output file, output option, then flag, sorry, and the output command and the executable file. Those who are running C.
Yes. उसमें ये फोल्डर जल्दी रन करने को सब लोग एक साथ बेसिकली हेडेक नहीं होता वो तो फोल्डर सेट अप नाम का फोल्डर नहीं है उसमें.
Okay, so one suggestion here to everyone who are using ParamVidya, since you are all accessing together, so you are editing upon yourself the same file. Okay, so just do one thing, just copy the files, make a folder for yourself and copy the files. Otherwise, you will be editing what the other have edited. Okay, so that will create a confusion. So just so to do that, just make a file mkd, make a file with your name, folder with your name, sorry, and copy the files there, all right, and then edit. Because what is happening, someone is editing, then again someone is running that, and there is a confusion. Okay, so anyone has issue with compilation still, compilation of the code? Everyone compile the code? Okay, so and for okay, so if you have to make directory because there is a same folder final, so all the guys are accessing the same file and editing it, so you can understand. So it's a confusion, so make a folder of your own and just copy the files. All right. Okay, so and for the guys who are online, you can just you don't have to do this job out and job all this. You can just compile MPI-CC and you can check. You don't have to use this jobs.sh file. Online, those are using VirtualBox or those who are having their own system. You don't have to use this script file or use see the answers from job.org. Okay, these are only for those who have access to the cluster. So everyone could compile. Is that side? Everyone compile that. Compile the code. Compile. Okay, great. So they said everyone compile the code, right? And just make your own folder because it will be confusing. So I'm showing how to run it one more time. Then we will just go through all the codes once. Okay. So you have got MPI. So I will repeat once more. MPI CC for the C files, and there will be some Fortran code also. So for that MPI F92. Okay. This is the compilation command. So this one is a C file. Some will be Fortran files. For Fortran files, you have to just replace MPI CC with MPI F92 for the compilation command. Okay. For any doubts, you can check the readme.txt. For any confusion, there is a readme file inside. Just check the readme file. It has got the compilation command, the job submission command also. So after MPI.cc, I'm repeating once more how to compile and run MPI CC hello world.c -o hello world. So I'm compiling it. All right. If I do ls, I will be seeing a hello world executable file. All right. Now I will be submitting it using the script file jobs.sh. This is for those who have access to cluster. Those who are running it in the virtual box, we have to just use MPI run minus NP, then mention the number of processes that you want to run on. So if you want to run it on 2, just mention 2, and then the executable name. So the executable name was hello world, right? So if I do this, you will be seeing hello world from process 0 of 2, hello world from process 1 of 2. All right. And those who have access to the cluster, just do sbatch, then the batch script file. The batch script file name is jobs.message. So if you do this, you will be getting a job ID. All right. So this job ID is unique to everyone who is submitting the job. Now to check the output, you will have to do. So the output is stored in VI, is stored in the file job dot the job ID name, which is 244p dot out. So you can see I have hello world from process 0 and hello world process 1 from 2. Till this, how many have you done? How many are able to do this? Please raise your hands. That's it. Till this part. Till this part. Running the code. Running the code done. Running the code done. Okay, so I hope we have actually come till this point where we can run the codes. Right? Okay, so we will be going through the code one. So Somnath sir has explained you the details of MPI, what are the introduction, send receive files, and also brought to us to then 1 or 2 codes for like Jacobi decomposition also I think he has showed. So I will be going through all the files and you can run it one by one. I will be running it too, and since everybody has been able to run the files, we'll do it together. So first is hello world, just going through the code. Okay, so as sir said, we have a MPI initialization. Then we are getting the rank MPI component. Just open the helloworld.c file using pi helloworld.c. So everyone just open the file helloworld.c using vi helloworld.c. All right. So anyone can use nano also if you are comfortable. And if this comment is shown, just do edit. All right. Just those who are getting that soft file option, just comment, just press E to edit. And one more thing, this will come because everybody is accessing the same file. So just make your own folder and copy the files. Okay. All right. So just to give a brief explanation here. So the helloworld.c file, please open it. So what we have done, we have initialized our MPI. Then we have taken the rank and the size basically means how many processes we are allocating. So it is basically mentioned by when we run MPI run minus NP 2. That 2 will be coming here in size. Rank starts from 0, right? So 0, 1, and then we are doing MPI finalize, right? So you can see. All right, so you saw that hello world from process 2. So let me just show it for how to change the processes. Okay, so this is for those who have those are submitting using sbatch. So just go to the file jobs.sh. Now you can see keep nodes equal to 1. All right, this is important. Just note everyone. So nodes equal to 1, keep it as it is. And enters I am using 2. All right. So let me use say 20. So I'm saying I want max of 20 processes from this node. All right. Now the command MPI, you can see here this command MPI run. It's the same command that we are using to run our file. And you can see here the option is MPI run minus NP $NP, $exe. So $NP and exe are two variables that we have created, which you can see here. Okay. So basically, exe basically is the executable name, right? So if you we compile hello world, and we mentioned the executable name as hello world. So that's why I have kept this hello world, right? And NP is the number of processes that you want. So now let's change this. So say I have a broadcast code here, broadcast.c, broadcast.n. All right. So if I just open it, so broadcast basically means what is you have. So to explain this, you have initialized, you have got the size of the number of total number of processes present. If you just go into the file or say see from the screen. So rank 0 basically says I'm assigning number equal to 1, right? And then I have done a print which is printing the number and the rank. All right. Then I'm broadcasting. Broadcasting basically means you are broadcasting the information from 0 to all the other processes. So if I after broadcasting, if I see the print, I will be seeing the number 1 is being sent to all the processes. Okay. So let me just compile it. So this is a C file. Compile it using broadcast API CC broadcast.c -o for the executable name. I am writing the executable name as broadcast. Okay, so it is compiled. If I just do ls to check, you will be seeing a green color broadcast executable file name. Okay, please everybody compile this. Now I will be submitting the job. Okay, so I have taken n task. Let me take 4. So just to run this, take n task equal to 4. Everybody. Okay. Then in the executable name, instead of hello world, write broadcast. Because broadcast is the name of the executable that we gave. All right. Next. Okay, let's run with 2 first. NT basically, I'm saying I want to have 2 processes. Okay. Is everybody able to change this? Okay, let me run this and then I will get back to you. So I'm doing smatch jobs.sh. So I get the job ID. I have to look into the answer. So just do job.2462.out. Just a second. Did someone access this file here? Something is saying.
Is that? Broadcast okay, so please everyone create your own folders. Okay, someone has changed the broadcast. I'm just running the wrong. Yeah. Okay. Please everyone create your own folders. All right. So anyone who is accessing this folder team1 final, please create another folder. This you can see what happened here is I was trying to run broadcast because I created the executable broadcast, but someone overwrote it using broadcast.o. So it was not able to find the thing. Okay, so let me just check this. So I have broadcast.o. Yeah, you can see. So you can see before broadcast, rank 0 and rank 1 had rank 1 had number 0, rank 0 had number 1. After broadcasting, it was sent to all the codes. So if you can change. So where is everyone able to run this? Who is not able to run this one? Change the file and run it. Okay, so everybody is able to do this. Good. So just try one more thing. Change the NP. Go to the jobs file. Go to the jobs file and change the number of processes. And make sure, so to do that, you have to mention here NP is equal to 4, 8, whatever you want. But be careful that you have asked for that much resources here. So if you want to run in 8 processes, make sure that you have mentioned that I want to run in 8 processes, and then do NP equal to 8. No, sir. Yeah, so I want to run. I'm now saying that I will run it in 8 processes. So just do hbatch jobs.sh. And you can see I have got the answer from 8 processes. So before broadcast, and also since the print will not be serial, right? So each process will run it in its own time. So it will not be serialized, like that rank 0 will come first, rank 0, rank 1 will be next. So you can see 0 to 7 before rank, and after rank 0 to 7, everyone had all the number 1. This everyone could do, changing the just rank. Anyone who could not do this? That's it. Could not do. What? This set everyone was able to do. Please say if anyone is not able to run the code. Change the number of ranks. Okay, since everyone was able to run this, let's go to. So we saw hello world. We saw how to broadcast a number from rank 0 to all the ranks. Then I will be showing you how to reduce all reduce. So if just go to the code all reduce.f.
everybody please go to code allreduce.f. So everybody is inside allreduce. Right, so let me explain this. So you can see we are having two variables here, pi and a1. Okay. So a1, what we want to do is, so this is allreduce basically it does what it. So you can reduce. So reduce you can use max. So you can take the max of all the. So say you have a number you have number 1, 2, 3, 4 in 4 ranks. Okay. And you want to take the sum of all of them and then give the sum to all the ranks. So this allreduce does that. You can take the sum, you can take the minimum also, max also. All right. So if you just go to this, if you see the example call MPI allreduce, you have A1. All right. So then in A1 is the number that we have. We want to reduce it and store it in A. Okay. Now we have only one since the size is 1. We have mentioned 1. Then the data type is real. So we have mentioned MPI real. Okay. Now the command, the command is we are reducing here. We are taking the minimum here. So you can see MPI min is basically minimum. If you do MPI max, it will give you the max of all the values that you want that is there, and then give the values to all the processes. Okay. And let me show you what is happening. So you can see A1. So A1, so the minimum will be given to all the processes. So just to run it, so MPI CC. Okay, so this you can see this one is a Fortran code. Okay, so do MPI F19 allreduce.f, not MPI CC. Please keep this in mind. Okay, then executable allreduce. Okay, now just go to jobs.sh file. Write the executable as allreduce and say that NP equal to 2 because I have taken n task equal to 2. So I'm saying I want just 2 processes. Then save it and do sbatch jobs.sh. I'm checking the output. Okay, now you can see the minimum was, so A1 had 1, right? In process 0. We have taken we have set the minimum, which is -4 to the power -8 to both of them. So now A has the minimum element, and it is stored in A in all the processes. So if just go to the code once more, you can see A1 was given here, and we wanted to store it. We stored it in A. So the minimum value that we got is stored in it. You can see the MID PY by n proc. So MID is involved in this calculation. That's why you are getting 2 different values. For MID 0, so 0 and 1 we have 2 values. For 0 we are basically getting 0, right? That's why that 0 value, which is the minimum of both of this, is transferred to all the processes. All right. So you can just check this for more than 2 processes. So to do that, just go to jobs file. Yeah, jobs.sh file. And say I want it for 4 tasks. So do n tasks 4. And here in NP, Okay, so someone is still using this file. You can see you don't have to do executable as allreduce.f. Someone who is doing this, you just mention the file. You don't have to mention it as allreduce.f. Okay. Let me compile it once more. So you can see, so I took 4 processes, correct? So from there, I got the minimum as 0. minus 0.707, and that was sent to all of them. Till this, everyone was able to do. Who was not able to do this part? Please raise your hands. Those who are not able to change the number of processes in allreduce and get the results. This side, everyone on the left hand side. That side, right hand side. Okay, great. So now we have seen broadcast and allreduce. Next, let's go into send receive part. So first example, there is a file which is send receive one.c. Please open the file send receive one.c. So we will be basically, so here what this code does is it will be sending a number from one process to another process. So first it starts with MPI initialization. Then we get world size is basically the number of process. World rank stores the rank of each process. So 0, 1 to whatever you want, n to nt minus 1. And this code will only run for, so just remember this code will only run for np equal to 2. So anyone who is running this for np greater than 2 will get an error. So all the send receives that I will be showing you after this, please run it for np equal to 2. Okay. Okay, so what it is doing is it is world rank 0. So the rank 0 is sending number minus 1 to rank 1. Okay, this is what this code is basically doing. So the MPI send, you just give the number, the location of the number. Then since we want to send only one variable, we mention 1. Number is int, so we are mentioning MPI int. And 1 is basically where we want to send it. So we want to send it to process 1. You can check this in the source PPT. So this is the syntax. First is the number you want to send. Give the number location, ampersand number. How many now? What is the size of that? So it's basically 1 integer. Then mention MPI int. Then third is where you want to send it. So I want to send it in process C1. Last one, this one is the tag basically. So we are just tagging this send receive as 0. And last is the MPI comp word. And world rank, what this is doing is this is just receiving the value. So you can see world rank equal to 0, I am sending. If world rank is 1, I am receiving it. Receiving is when receiving also I'm storing it in number. So you can this number is present when I do int number. This is the parallel code. Int number is in all the processes, right? So number I initialize number 1 in world rank 0 only. So if condition, this basically means number equal to minus 1 is in world rank 0. It's not in rank 1. So after that, when we do receive this number, we are storing the value that has been sent by 0 in number itself of rank 1. So the syntax is this, the number of how many values you want to send, the data type, from which rank am I getting the values. So I'm getting it from 0. So it is 0. This tag should be matching. If you don't match it, this should not happen. This transition should not happen. MPI com world and MPI status ignore. Okay, so we should basically get -1, the answer from this. Let me compile it. So it's a C code API CC send receive. All right, then go to jobs.sh. So remember, end task should be 1. Any send receive code, those who are running, please remember end task should be 2. End task should be 2. Otherwise, it will not run. So my executable was send receive 1 and NP equal to 2. Right, please make these changes. So the answer you can see, process 1 received number 1 -1 from process 0. Right? Any doubts here? Those who have doubt in this one, send receive. Everyone could run this. Anyone who could not run? Okay. So this is one example of just when we were sending a single number from one process from process 0 to process 1. Now you see there will be another code which is send receive 2. Everyone completed send receive 1. Anyone who has not completed, please raise your hand here. Okay, great. So send receive. So send receive 2. Please open send receive 2 5. So previously in send receive 1, we were just sending one number from process 0 to process 1. In this one, what we will do, we will be sending 2 numbers. Okay. So first, so as usual, we are initializing, we are getting the rank. We are initializing, we are saying that if the total number of processes is greater than 2, it will not run. Then coming to int number. So if vol rank equal to 0, we are mentioning the number equal to -1. Okay. So next we are doing what? We are sending this number. And the syntax is same as the syntax used in the previous code, previous and receive ones. Now you can see we have then done one receive also. Okay. Now just see one more thing. In the vol rank 1 case, if else if case, I'm receiving this number. So how am I matching this? This tag, 0 tag. So you can see the MPI send has 0 tag in vol rank 0. When I'm receiving this, I'm keeping this tag as 0. Correct. So this is how it's able to match it. Now then you can see what I'm doing. After receiving this, I'm stating the number is -2 in the second rank only. All right. So after vol rank 1 gets number equal to -1, I am stating that number is -2 now, and I will be sending number -2 back to the first process, the process 0. So here you can see send number, the same syntax, just the tag is different here. I have changed the tag to 1, and then it is receiving here, and you can see the tag has been changed to 1. All right. So let's run this code. So MPI. Compile it, then go to jobs.sh. Someone already has received 2. Okay, so you can see the answer is process 1 received number. So first process 0 send number 1 to process 1, which it received and it's showing. Then what we did, we changed in process 1 the number equal to -2, and then we send this number -2 to 0. So you can see process 0 received -2 from process 1. All right. So the sequence, so send receive, as sir mentioned before, send receive is basically blocking. So there has to be a like handshake between the send and the receiving process. So if you change the sequence of the send receive, you can do it yourself. If you just keep send above, receive below, and do all that, it will not run because it's a blocking case. Anyone having issue with this running this one? Great. Next we have, you can see next we will be sending arrays. So basically we were sending now just single numbers. Go to the file send receive array.c. There is a file send receive array.c. So there we will be just sending whole arrays because previously we were sending numbers. The initialization all that's are same. Now come to this part. So we'll be sending an array of size 10. Integer array. So we initialize two variables, two arrays with count. We define two arrays, two variables with count. And in world 0, so we process 0. What we do is we say that num i is equal to I. All right. So we initialize it like that, and then we send it. Here also the send receive is we are sending and receiving arrays from both the processes. Okay, you just open the send receive array files. So here also we are sending and receiving arrays from both the processes. So first we are sending num. So num has 0, 1, 2, 3, 4, right? Now 0, 1, 2, 3, 4, 9. And in world rank 1, what we are sending whatever num that we got. So from rank 0, we are doing count minus I minus 1, right? So basically, so if num 0 had 0, what we will send, num 0 will be getting 9. So 9, so num 0 will be 9 when we will send this to process 0. Just check this once, compile the code and run it. Okay, so just see the output here. So first we had num, which was num 0 is 0, num 1 is 1, num 9 is 9, right? So we sent that to process 1. Then process 1 received it. Then it changed num to count minus that number. So basically num, the number 0 become 9 now. Num 0 is 9 now because count was 10. And then it was sent back to the process 0. You can check here. So num 0 was 0, 1, 2, 3, 4, 7, 8, 9 from process 0. Then we changed it to count minus I minus 0. So num 9 has now 9. Previously it was, sorry, num 0 is now 9. Previously num 0 was 0. So this is an example of sending and receiving arrays from both the processes. So doubts are here. Any doubts here? Anyone? Everybody got this answer? Output. Should I go to the next one then? That side got this output. The previous send receive array output. Okay. Okay, now let's go to send receive I send. Send receive, there is a send receive array I send. .c. So the file is send receive array I send.c. So those who are online can ask the questions in Q&A. If you have any doubt, please write it there. Then we can clear that. Okay, so everybody in send receive, I send. Please open that file. So previously, the previous example was send receive blocking. So there was a need of an handshake before the sending and receiving to acknowledge there is a sending of data and receiving of data. I send I receive is non-blocking. Okay, so if you just go through this, we are doing the same. We are doing the same thing as before. We are sending two arrays. Now in this case, in send receive I send, you can see I send and I receive are like one after another. If I go to the previous case where it was just send receive, not I send and receive, you will see first we had send receive. First we had send, then we had received in world rank 0. And in world rank 1, we have received then send. Right? So the sequence is necessary in this blocking case. But when we go to I send is non-blocking. And you can see I send and receive, we are not keeping that sequence. So in process 1, previously it was I receive, then I send. Right? So this is not kept here, and you can just run and see the answer will be correct. There will be no error in this. But if you try the same thing in the previous code, just copy, just change the sequence, it will fail. Okay. Okay. So how to understand this code is running? This data, the answer data correct should be 1. Okay. So data correct, when you run this, if data correct is 1, that means all the data has been sent and received correctly by both the processes. You can go through the code part. It is fairly easy. So if num1 equal to count I minus 1, then data correct is 1. Data correct is 1. And if it is not, it is 0 and it breaks. Right. So if you just check the answer. Yeah, so the answer you can check. So
every time I'm doing that, getting the answer same right? No process is done.
I think you are editing this here only, right? Or have you created another folder?
Yeah, it's another folder.
Okay, just sit up. So any doubts here in I send and receive, you can check the answer. Process 1 receive correct data from process 0. 1 means the answer is the data exchange is correct. Any issues till here on this code? Those who could not run? Anyone here? Compilation. Online participants, please mention if you have any doubts. Please write it in the Q&A. Those who are running in Ubuntu like VirtualBox, please don't need to do SBATs and all that. You have to just do MPI run. Dispatch, read, job dot out, all these are for those are using the cluster, but with their cluster. Alright, you can just run your code, run the commands. The commands is in the readme.txt file, readme.mpi.txt file. So those are using VirtualBox and all that. There is no, those are not using the cluster basically. You don't have to use sbatch or the job read job.out commands. You can directly run the commands. Any doubts till now, other than running the code? Anyone having those, please raise your hands. And please mention in the Q&A online participants. Should I go to the next one? Any? Okay. Yeah, excuse. Hello?
STD equal to compared to software.
Oh, you have to put that. Nandan.
STD equal to
They do
99.
99. Okay, so some of you guys are getting an issue with compilation with std gnu. So please mention minus std equal to gnu 99 inside the compilation line. So basically, when I'm compiling MPI 60, this one, right, minus std equal to gnu 99. Right? Those who are getting this issue. For those only for those who are getting this issue, not for everyone. Some compiler modules has been done. Anyone still stuck here in this one? Can receive? Here, anyone stuck here? This side? Last one, send receive, I send, I receive. Or before anyone is stuck, before also. Okay, then I'm going to the next one. Okay, so there here is okay. Open the file data mismatch. Send receive data mismatch. .c. Everyone open the files, and from the name itself, you can understand the issue is there with the data type of the data that has been sent. If you just look into the code here, we are sending MPI double, right? But we are receiving MPI close, right? So just compile this and check. I think this will not run. Just compile and run this. So if you compile and run this, just run the data mismatch one and see what is the answer you get. You will be seeing that there is an error that has occurred in MPI receive. It will not run. So if you run this, you will see there is no output visible. And the error, so you can see the error in VI, that same job dot your job ID dot ER. This will show the what is the error. Okay. So in this you will see there is no expression. Okay, there is a question regarding MPI, which is saying that why MPI is MPI wait required. So in a blocking case, what happens? If the processes wait until the handshake happens and they take the data transfer and they realize the data transfer. But in this I said there is no they don't wait, right? So if you don't keep a MPI wait, what will happen? The transfer might not have happened, and you have gone to the next task, which involves the number that you have used in send receive. So if the data transfer has not happened and you are using it, you will get a wrong answer. So that MPI wait is necessary, and we will see that the parameters are request and status. So this request and status are present in MPI, ISEND, that parameters, right? So these are so MPI wait checks that the transaction that the send receive has happened, and then lets you go to the next task. So in case if you say if you have a task which doesn't in after this send receive I send I receive. So this question is pertaining to the I send I receive one. Okay, if you okay, so if you check this was the I send I receive case. The question that the saying is this MPI wait necessary? So it is necessary. So but the thing here is we have also given MPI barrier here. So if we the MPI barrier itself will stop all the processes. So in cases where we don't have MPI barrier, MPI wait is necessary. You can also like play with this. If the next job if this job doesn't require num or num1, okay, then you can keep MPI wait after this also, where just before where the data is required, the send receive data is required. Just to be sure that the send receive has happened, the data transfer has happened between the processes. Okay, so everyone has done the last one, send receive, which was not working, so you'll be seeing no output basically, right? And if you just so you can check if this works. So just go to the file instead of MPI. So it's MPI double MPI float, right? In this so it is MPI double and MPI float. You can just change it to MPI double both and check if the transaction is happening. Right? You can just change MPI double here and run it, and you will see it is running. Okay, now since we have done like we have checked hello world, we have checked the broadcast, how to transfer data to all the processes, how to get data from all the processes, reduce it and then transfer it back. We have seen the blocking send receive. We have checked the non-blocking I send I receive also. Now and the data mismatch cases where it fails. Now let's look into some. So let's look into some applications of this. So there is one. Okay, one more example. You can see pi.f. So pi.f basically it's calculating the value of pi. Okay. So it is dividing it. So this task is divided into different processes using my ID, right? Now what happens at the last? We need to, if you just go into the file, we need all the values of the sum of all the values together. So this is in case of all reduce. All reduce basically means I am calculating. So I have pi. I have calculated pi in all the processes, but at last I want the sum of all the pi's. So instead of doing send receive, so if you in for two cases send receive is okay, but if you have say 1,000 processes, you cannot do send receive for 1,000 processes, right? So in that case, what you will do, you will say all reduce. So what does this mean is this pi value is in all the processes, is present in all the processes. We need the sum of all them in all the processes, the sum of all the pi values. So what we do, we take the sum in pi sum value, which is present for all the processes, and we write this MPI sum function. Previously, if you remember, we did MPI min, which was taking the minimum of the values. So in this case, we are taking MPI sum. So what it will do, it will take the sum of all the pi values from all the processes, store it in pi sum, and then send this pi sum to all the process back to all the processes, right? So if I just compile this. So compile this is an F90. This will be F90 since the Fortran code. So you can see the real value of pi is 3.145. So it has calculated, right? So just check once. Okay, let's now go to now we'll be seeing like how to. So sir gave an example of Jacobi decomposition in your code, decomposition of the domain and then giving that domain to different processes. Okay, so we will be seeing such an example here. So first go to the file Jacobi single process. Just go to the file Jacobi single process. So here what we will do, we will change the, so we can do a lot of things with this case. You can, if you go to into the file Jacobi single process, you will be seeing number of steps x, number of steps y. So basically the domain here is x into y, 1000, 100 into 100. All right. And this will be divided into processes. So let's start with a small case. So say I have 10 into 10. Okay. Run this code and check how the timing is. So there is a timer given here. So let us run this code. So this is basically a single process, but since we have included the MPI MPI's folder here, we are running it in, we are compiling it using MPI CC, but we will be using NP1. Okay, this is a single code case. So .c. Okay, you will get two warnings. No need to bother about that. And then do the run. So you can see the time taken here is, you can see the time taken by this is 0.02030. So the convergence, so we look in till 1e minus 5. Till 1e minus 5, we check the time. How much time it has taken, how many iterations it has taken. So this is a single process case. Okay. First, everybody just run this single process one and get the timings. Okay, and make NP equal to 1 in this case because we are running a single process case. So we are getting time 0.02. We had, if you remember, we had the total domain as 10, 10, right? 100. Let's increase this and see how much. So let's make it 2020 or like 50. You can see as expected, the time taken is more. So we had we had 10, 10, 100, right? So we have increased 25 times. And the time taken is quite high. So, but this don't look using docs.s and get the time. So you can see this is the timing that I got for 4.8. This was for 50 plus 50. Now you can just say let's double it. Like let's see what happens. So this is single process. After this, we'll be looking into the domain decompositions where we will be dividing this domain to number of processes. So let's just do. 50, let's just double this. Okay, one more thing, please compile after changing the number of steps each time you change it. Okay, please compile the files. So you can see so this is 4 times basically. We had 50. So you can see this is quite slow. All right. And one more thing you will notice that when you run this code, you will be seeing that the output file, you are not getting any output. Because this will take time to write to get the output file written in that to the output written in that file. So just wait for some time and you will get the output. So you can see here it is taking quite a lot of time. Previously it was 4 seconds for 50 plus 50, 4.8. Now we just did 100 cross 100. Okay, so let's now do the domain decomposition case. So just go to Jacobi domain decomposition.c file. So if you remember, we had 50 plus 50, we took it single process to about 4.8 or 4.4, something like that, for 50 plus 50. So if you just look into this, so this is the case where I ran the same 50 plus 50, but with 2 processes. Okay, so you can see the timing is 1.47. Previously, when I ran with a single process, it was 4 point something, 4.4, 4.8. Okay, just check. So now say if we increase, okay, now we can check 2 things there. What will happen if we increase the process? And second is what will happen if we increase the load, increase the size, the grade. Okay, let's start with increasing the process. So if we make instead of so if you have 2, so if you make it for will it be half, you can check this. So So it's half, actually less than half, right? So we can do one thing, we can continue this, and at some point you will see it will not be half, it will not half. That is because at that time that thinking between the processes will take place. So it has to. So let's see. Let's just check this. So it's 0.5 now. So it is again half. So it is again half, right? Let's take 16. Let's take 16. So please try yourself also. So those who are in team 1, they might not get access because I'm using it. To other teams, you can try this. So let's 6. So you will get 16 and you have 48. So we'll get 32. So but approx is not like previously it was more than half. Now 16, let's go one by one. 60, but we cannot do in this one node category. We have to take 2 nodes. So let's say 32. Almost like, but it is not half actually. It was 1.1 before. It's 1. So it's not actually half. But if we let's take the maximum we can get. So we can get 48 here. It was not that much. So basically, if you take 64, you will see that it will not scale that much. It will not be hard. You can try this later. So this was we were having the so this was for 50 plus 50, right? So if you remember 50 plus 50 for 2 was 4.4. So let's 200 and take okay, let's start with the 48 one. Remember 40, 0.07 something was there. So let me compile this. So it is for almost 0.07. It was 0.44.
6 times.
So we increased actually how much? 4 times.
0.07 to 0.44.
We increased the load how much? 4 times. 50 to
6.
The load 50 plus 50 50. We made it 100.
4 times.
4 times we increased it.
Increase by 6 times. 0.07 to
0.07 and 0.4. Right. So let's now see that if this is scaled. Okay, so we have 48. Let's do it 32. So it's taking time, you can see. So So it's 0.48, 44. So it is not scaling. No, let's see it's 16 actually. And we can understand. So this from this time you can see it is scaling from 16, right? So so like this, if we go, we will get 1.8 for 8. If we let's see that, let's say that. We are getting more, right? So you can see if we, for 8 we are getting 2.6, and when we are using 16, it's 0.9. 0.9. So from here you can see what is that optimum load and what is that optimum process that you have to check. So you can all check yourselves. Please run the code yourselves. And also you can check like how much is the total complete load it can take. Like this is 100 cross 100. You can check with 500 cross 500 also. But it will take more time. You have to be patient to get that result. Okay. So please run this. Please. Did anyone try to run till now, or anyone ran the code? Please run this code and check what check with. So we have done 100 cross 100. Change it to say 200 cross 200. So in the Jacobi domain decomposition.cts, change it to say 200 or leave it to 100. Let's leave it to 100 now. Leave it to 100 and run. And the best would be if you run with NP1 at first, NP1, NP2, then 4. Then you will get the actual speed up. How much more like faster? How much faster is your code getting compared to the one? What is the speed up? Okay, so keep number of steps 100. But if you want, if it's taking more time, reduce it to just 50. Okay. You can say one more thing also. If you have very less, say 10, it will take more time. And if you increase the process, it will take more time. There will be no speed up because so the workload is so less. There is no point of dividing this workload into more than one process. All right. So just change this. Change this, and in the jobs.sh file, please be careful to change the end tasks. Okay. If you're keeping end task 8 and you're requesting for 16 processes, it will get an error. Change the end task and also the NP. And try with NP1 at first. Keep 50-50 and try with NP1 at first.
स्केलिंग क्यों नहीं होता? 50 में 48 एक ही रोज होगा.
Okay, okay, so let me just explain this a bit. So a bit explanation of the code. So what MPI does is we run the process in parallel, right? So if you have a single, so this basically solves the Jacobi process. So we solve a particular function, you can say, on the complete domain. Okay, so domain is basically domain has number of points, which is number of steps x into number of steps y. All right. So just see that there. So we have this. The complete domain is number of steps into x into number of steps y. All right. Now we want to solve a particular function on each of these nodes. This is the task. Okay. Now we do it serially. We have to go. Say it's a for loop. In the for loop, we are going through. So this for 200 into 200 points. We have to go right for a single process. So this will take a lot of time. Domain decomposition, what it is doing is we are dividing this complete domain into parts, and this parts is basically equal to the number of processes that we have. So if you say NP is equal to 2, we are dividing the domain into 2 parts. If you say NP equal to 4 parts. And what is happening is all these parts are calculating that for loop or that function parallelly. Right. So what is that? So you can when we are increasing from 1 to 2 the process, the time was getting half. Why? Because both the things are happening at the same time. So we decompose the domain into 2, and that happened in parallel. So the time was getting half basically. Right. So if we decompose the domain into 4, the 4 things will happen in parallel. So say for example we have so this is 200. Let's take a small domain. So we have 100, right? For a single process, normally what we do, we have a for loop, which will loop over 100 elements, and something will be calculated, right? What domain decomposition does is this 100. So we have 2 processes. We'll divide it into 2 domains, right? So 2 domains basically means 50-50, right? So each process, what it will do, it will loop over 1 to 50. But it will be done simultaneously. So there will be a saving of time. Obviously, there is a transfer of data that is needed. So as you can understand so 1 to 50 is in one domain. 51 to 900 is in another domain. But to get the data of 51, you need to give the data to the other process, right? Because the other process doesn't have 51. Or for the same reason, the first process doesn't have the data of, the first process doesn't have the data of 51. Similarly, the second process, if I have 2 processes, doesn't have the data of say 50. That's 50, right? So there will be a transfer of data. There will be a boundary of the transfer of data. Okay, of the domains to just have to synchronize. Otherwise, there is no point calculating because it will be wrong data. So you can understand. So say if you have a lot of processes, okay, just an example when the case will not scale, so when you will not get speed up. Say you have a small domain and you have taken say many processes. So what will happen? You have to transfer the data, right? So that other processes know what is at the boundary. So you can see what it is showing. So if you have a complete domain and we have divided into 4 processes, right?
So we have divided into 4 processes. So we are solving in 4 processes. So each process will solve only one, but we don't know the data of here. So when we need the boundary condition here. So what happens here? What happens here is that we transfer the data from here to here. When we are solving this, we are sending data, and this domain is receiving data. So receiving is basically we are transferring the data between different domains. Similarly, when we are solving this, the data is transferring from the boundary data is transferred from domain 1 to 2. Similar occurs between all the domains. So why it was not scaling well after 50 process 50 when we are giving number of process around 48. So only one cell in one domain there would be only one cell. So most of the time actually it is executed is consuming the data transfer. So data transfer is always in overhead. So after some time, depending on the problem size, you will hit a ceiling that it will not accelerate much.
Yeah. So
balance.
Yeah.
So for that you have to do load balancing.
Yeah. So load balancing is one case. So what is basically load balancing means is we want to divide the data equally to each process so that they take similar time. Because if we don't have load balancing, say in this domain 1, 2, 3, 4, we give 1, 2, 3 to a process 1 and the 4 to process 2. So one will obviously take more time, and there is so it will.
If the domain says that unequal, then we have to do load balance and divide the domains likewise.
Theoretically, if we have a big data, at one point it is converged. If I'm increasing the like 32 to 48, 60 for some number, at some point it will converge. But can it go in the reverse way? Like it is improving, the time is improving. It will converge, but can it go to the negative because of how much boundary conditions?
It will increase, right? Time taken will increase. It will not like. So basically, what we are saying is we have increased the processes so much that the more time is taken by data transfer instead of the
Rather
calculation.
than solving the problem, more time is consumed by the data. 60 or 60 are into 2 minutes.
64 to like 0.05 seconds. But at 128 also it's at 0.05 around. But can it happen that if I make it 250,
It is increasing.
0.06?
Yeah,
It can happen.
it can happen. It can happen that it might take more time.
So there is one part also. So here the domain decomposition is in one direction. All right. You can do decomposition in multiple directions.
Multiple, we can also decompose the domain like this. So, but we have to actually transfer data. We are only data, but single block will now be transferring data between two blocks. So that can also.
So one thing is you have to calculate how much at the surface, at the interface, how much is the communication cost and how much is the computation cost. So if you might, so one can say like if I divide the data like this, it will work better because there are 4 partitions, therefore, but you have to take care of the communication cost also. You cannot just go on dividing data, right? So that is also one thing. In this case, we have just divided in a single direction. Any doubts, anyone? So in the code, basically what I was saying, the code is, so the domain is basically, domain name given X and Y is 1. So in a 1 plus 1 domain, we are dividing it into parts. So 10 plus 10 means we are taking 10 parts, so 100 points. And then this is all okay. Now next we are doing the calculations here. So okay, the node. So one more thing you have to take care is that the starting and ending point. You have to mention the starting and ending point of this, right? So when you have to send this, you have to let them know that which is the starting point. So for a single domain, starting is 0, ending is 100. For a multiple domains, it will be different. So as you can like just call a single variable and do it, you have to give this node x start x end like that. So as that node x start means basically the start of every domain. So you have to calculate that properly, right? You have to check that. So here what we are doing is we are calculating that start and end of each domain. Why do we need that? Is basically for that for loop to happen. You have to need the start and end, right? So that's one reason, and also for the send receive, you need to know where the send receive is happening, which part you want to send and which part you want to receive, and that will basically be the part where it's starting and where it's ending for the middle blocks, and also for the last blocks there will be send and receive in one direction only. For 2 and 3 there will be send and receive in both directions. Okay. Okay, so this line here. So line 160 to 170 is basically the for loop that I was saying to you. Okay. This is the for loop that is happening over all the processes. All that is happening, and that is the calculation. And here you can see double send to R is basically the send receive, how much data has to be sent and how much data has to be received. This is the calculation that has been done. And here the send receive has been done. MPI send to R is basically sending to the right side of the domain, sending to the left side of the domain. And similarly, receive is also there. And we are, and you can see wall rank. So what we are doing, we are taking the even odd thing. So if it's even, we are sending first. If it's odd, if the process is odd and even, if the process is even, which is here, we are sending it first. If it is odd, we are receiving it first, right? Because if you remember the send receive thing that we showed you, right? There has to be a sequence maintained. If we just do send first for both cases, it will not work. So this is overall, this is the code. You can go through the code yourself. It is fairly simple. And at last, the error that you have seen, you can see there is an error printed. Iteration error. So the iteration. So with the local error, we were calculating in each domain. And then what we did all reduce so that we could calculate the global error, which is the maximum of all the errors, right? From that, we could print the error. So if you just say I'm printing local error, that will not give you much, that will be not much sense, right? One will be different to another. So we need a global error. So that is what is happening here. We are calculating the global error and storing it to all the processes. And then we are printing. Printing is done only in one and zero, only one process. And at the end, here we are just taking the. So here what we are doing end W time, we are taking the time. Okay, end time is basically saying how much time has been taken for the whole thing to be done. And this has also to be done, all it has to be done for the same reason, because all the processes will have their own end time. So what you have to do, you have to take the max of them. Okay, not the sum. It has to be the max because they're happening in parallel, right? So the timing should be the max of the timing, not the sum of the timings. Okay, so anyone ran the code? In small, anyone ran the code? Please put your answer. Domain decomposition, anyone ran the code? Okay. Please check if you please run it and see. So this is one example of domain decomposition. So basically we have a domain and we are dividing it. There is another example which is data decomposition. Okay. So what we are doing, we are dividing the data. We are dividing the data instead of dividing the domain data. There are two. So an example here is so this a variable. Go to the file MPI cg.fn. Okay. So previously we were decomposing the domain into parts. Next, what we're doing, we're decomposing the variables we have, the data we have, into parts. Okay. So say I have A. Similarly, I'm calculating the start and the end, and that only that region of the variable is being calculated by a processor. Right. So example here basically is so in 32 in MPI cg.f95 we have a 2D array A. Okay, so A is basically you can say Aij, if j is equal to 1, then Aij is 5. This is the simple definition of this, and this is n. The total size is n square of this, where n is given here 10,000. Let's see, reduce this a bit. So, and we have taken a b also. So basically, this is solving a system of linear equation. Okay, this thing is solving a system linear equation. We have a. And we have b here, which is ax equal to b. So this is the b part. So b is basically j. Bj is equal to j. So this is a dominant system. Okay, and so this is basically a dominant system. We are solving ax equal to b. We want to find x. So we have a here, we have b here. And what we are doing this n local, n by proc is basically the number of local elements we have. N is the total, which is n is 100, 10,000, and proc is basically n proc is number of processes that we have. Then we divide it. So if you see line number 103, you can understand in line number 103 whatever thing I start and I end. Okay, so the I start and I end part is the start and end of each part which is assigned to the process. All right. So this is how we are decomposing, and you can see I is here of A I Z. So this decomposition is done only. So we have chunks of rows that has been taken, and that's how we have decomposed it. Okay. And then we have taken the sum here. We have done all together. And at last we are getting the answer. So this is this part below is the system, how we have the solver, which explains the solver. The main part where we have done the data decomposition is given in 130, 103 and above. Here, 76 to 80 and 50. And 50 to 60. These parts will show you how we have done the data decomposition. Altogether is an example of where we gather all the values from all the processes into the system into 0, and then we give it back to all the processes back. Right. So let me just run this. Oh, wait, just a second. So let me reduce the total, and it's quite huge here. Okay, time taken is 1.4 into 10 to the power minus 3 seconds. If I just do 4, let's see how much it is. It's 3, right? 3.5 into 10 to the minus 3 seconds. So previous it was 1. That means, so let's do one thing. Let's increase the data. Increase the data chunks we have. So this is not even 50. 200 plus 200 is also not a right load to for this case. Okay, so you can explore this. Which one is the right case, and you can also decompose it in more than one way. Okay, so this completes most of our examples. We have shown all the synthesis, all gather, reduce, and so decomposition, data decomposition. If you have any doubts, you can ping us in the Q&A, and also you can reach out to us. Thank you. You can have tea, I think. So session has been completed. You can go and have tea outside.
So that's an announcement that there will be offers in the evening session. So you will be able to. Tomorrow morning bus will be there, also tomorrow evening bus will not be there. And also during the morning, please be on time.
Thank you for offering.
Because it's holiday or Christmas, but tomorrow morning we will get bus.